All right, this is 9.5, the composition of functions. So far in chapter 9, we've looked at the sum of two functions, the difference of two functions, the product of two functions, and the quotient of two functions. So now we're looking at the composition of two functions. So kind of the same thing in a sense where you start with two independent functions and you're combining them. This time we're combining one inside of another. So if you can imagine one function, let's say, is x plus 1. So f at x equals x plus 1. And you can imagine another function, g at x is equal to just x. So now we're taking the x plus 1 and we're putting it in the x value of the second function. Okay, that's kind of just very brief explanation of what we're doing today. So determine the composition of two functions numerically, graphically, and algebraically. Ramon?
Sometimes you will find a situation in which two related functions are present. Often both functions are needed to analyze the situation or solve the problem. Forest fires often spread in a roughly circular pattern. The area burned depends on the radius of the fire. The radius, in turn, may increase at a constant rate each day. Suppose that A at R equals pi r squared represents the area A of a fire as a function of its radius, r. If the radius of the fire increased by 0.5 kilometers per day, then r at t equals 0.5 t represents the radius of the fire as a function of time, t. The area is measured in square kilometers, the radius is measured in kilometers, and time is measured in days.
Okay, how can the area burned be determined on the 6th day of the fire? So this is a great, really simple example where we have two functions. One is for the area, which we all know is pi r squared, and the other one is a function that relates the radius to time, so the amount of time the fire has been burning. Okay, so this is a great example. So we're going to see how we're going to take that radius function and we're going to substitute it in to the r value for the area function. So that's what we mean when we talk about composition of functions. So first of all, we're going to look at what that looks like graphically and a numerical analysis. So we create a simple table of values for the first function. We have our time in days and we have our radius calculated. Very simply, we take time and we multiply it by 0.5. So that's a very simple table of values. We can make a very simple line graph with a slope of a half. Next, we take our...
Pardon me, I'm sorry. Mr. Moser, please contact the office. Mr. Moser.
Next, we take the values that we determined from the first function, right? The calculated radius values or y values from the first function, and those become our x values of our second function. Okay, so that's why these y values here are now our x values, because we're substituting in the radius for the radius in the second function, which gives us the area. Okay, so then we just make that simple calculation, pi times r squared. All right, so if they want to know on the 6th day, we can go down here, see time is 6. We know that our radius is going to be 3 of our forest fire. We're going to substitute that in for the radius of the forest fire, and then we do 3 squared is 9 times pi is 28.27. So that's the area of our fire. Any questions about that? Okay, pretty straightforward. Here's what that looks like on a graph. The first one, as we know, is just rt is equal to 0.5 t. So that's a simple linear function with a slope of 0.5. The next one we have is our area, where we have a quadratic. Okay, so we're looking, of course, just at the positive values of the quadratic because radius can only be positive. Okay, so we have this parabola happening and we have this straight line. Okay, so that's what they look like graphically. Finally, at 6 days, we can go at 6 days. We see the radius is 3. So then we need to look at what is the value of the area when the radius is 3 on the second graph. So we go to 3 and we move up and we can see that the area is 28.27. Okay, so there's graphical table of values and then graphical. So here's just a summary of what I mentioned. The output in the first table becomes the input in the second table. Okay, time gives us our radius, radius then gives us our area. Any questions? That's the composition of one function within another function. All right, algebraically, of course, the solution type that I prefer personally, it's usually much quicker and a lot more accurate. So using algebraic analysis, we want to know what is the area, again, of that fire after 6 days. So this is how you need to consider it. Okay, the area is F at R, where R, the radius, is determined by the y value of the first function. So that's what we sub in. So we sub in g at t for R. Any questions about that? Because remember, g at t is just the y value of the radius function in function notation, right? So we're substituting in the y value for the x value. So this is an algebraic representation of what we did here, right? Any questions about this formula? You got to understand what went on here. Okay? All right, no questions. So now how that looks algebraically, I'm substituting that g and x value. We know it's 0.5 t, so I can just sub in 0.5 t. And then I develop this new equation, which looks like this. This is the function f composed of the function g. Okay, so it's a composition function, right? And then we can take our time value, which is 6, and substitute it in directly. Or sorry, I think it's 6 or 3? 6 days. Sorry, yeah. Substitute that in directly. Okay, and we get 28.3. Algebraically, much, much faster, much simpler. No table of values, no graph required. We just couldn't perform it algebraically. Yeah.
How did pi bracket 0.5 t go into the next step? 0.25.
Oh, because 0.5 squared is 0.25. Okay, and then they just put the pi behind the 0.25. They just changed the order.
Okay.
Okay, so it's like this, right? It would have been pi 0.25 t squared, right? After I square both of these, 0.5 squared is 0.25, t squared is t squared, right? And now they just changed this to 0.25 pi t squared, okay? They can move these around because it's multiplication, right? 3 times 5, same as 5 times 3. Okay, any questions with that? All right. Reflecting questions are not very helpful, so let's move on. Example 2. So given the function f at x is equal to 2x plus 3, and g at x is equal to root x, determine whether f, the composition of f of g, is equal to g, the composition of f at x. Okay? So in other words, what we're asking is if I substitute the y values in of g in my f at x function, is it going to be equal to, if I substitute the y values of the f at x function into my g at x function? What do you guys think? Just kind of what's your natural instincts? Are these going to be equal? No, I wouldn't think so either, right? If you take this value and you sub it in for this value of x, are you going to get the same value if you take this value and sub it in for this x? No, probably not, right? Okay, so let's see what happens. So here's what we call the outer function, and here's the inner function. So we're substituting, when you have the nomenclature where the f is first, it becomes the outer function. The second function, letter g, that becomes the inner function. And the way you would read this is f is composed with g. Okay, that's how you read that. F is composed of g. G is composed of f at x. Okay, that's how you would read this. All right. So very quickly, let's see if our instinct is correct. So when we have f is composed of g, we're going to substitute in root x, which is the value of g, for x in the f at x function. So wherever I see x in the f at x function, I'm going to sub in root x. So I get this value. Okay? So my f composed of g is equal to this. Okay. Similarly, when I compose g of f, so g is composed of f, now I'm going to take my f at x value, or my y value of my f at x function, and I'm going to substitute it in for my x value in my g at x function. So that's what I'm doing here. So g at 2x plus 3, because that's my f at x value. I'm going to substitute that in for x in my g at x function, which is root x. So I get this. Okay, and we can clearly see that these two are not equal. All right, so the order then does matter. Okay, so when you see a multiple choice question like this on a quiz that you might have next week, and it asks something about the order, does f at g composed of g equal g composed of f? The answer is no, it doesn't. Okay, they're not equal. Okay, and there's the reasoning behind it. All right. This maybe is the most difficult part of today's lesson. It's the domain, okay, and how the domains relate. So it says reasoning about the domain of a composite function. So let f at x equal log 2x and g at x equal x plus 4. It says determine f composed of g and find its domain. All right, so f composed of g is simple enough. We're going to take the y value of g at x, which is x plus 4, and we're going to substitute that in for x in our f at x function. Okay, so log 2x becomes log 2x plus 4. So we're just taking the g at x value and substituting it in wherever we see x. Okay, any questions about that? How I get f composed of g? That's pretty straightforward, right? F composed of g. Okay, now the domain we can get in several ways. One way we can look at the original functions, and actually we should do that always. We should see if there's any values of the original function where the domain is undefined. Okay, but we can also look at the composed function, so the final function, and we know here that x plus 4 has to be greater than 0. Okay, that's by definition of the log function, right? You can't have log any base to a negative number. Okay, we've talked about that before. It has to be positive. So therefore, x plus 4 has to be greater than 0. X is greater than negative 4. So that's our domain of our composed function. Any questions there? No.
No.
Okay. So B. What is the relationship between the domain of f composed of g and the domain and range of f and g? So this part is interesting. To be honest, I could not figure out this diagram. I looked at it for not too long, but it doesn't make a lot of sense. I can understand the rest of it, but this diagram is quite confusing. Okay? Sometimes they make a stretch to make things visual. In this case, it's one of those kind of algebra-style situations where it kind of doesn't help. All right. So let's look at the writing here. The domain of f, which is, this is our function. Here's f, log 2x. We need to recognize what that function looks like, right? Right, that's our function for our logarithmic function. Okay, so we know that our x values have to be greater than 0 for f at x. So that's why we have our domain here listed as 0 to infinity. Okay, in other words, x is greater than 0. Range we know goes off, into infinity. So y is yer. Okay, actually. No, I drew this wrong. Can you get a negative y value for a logarithm? Somebody do on their calculator, just do log, like log 10,000. I want to see if if there's a horizontal asymptote. I can't remember. Anybody? Nobody? It's 4? Yeah, so we won't get a negative number. So there is a horizontal asymptote here, so y has to be greater than 0, right? I don't know why they have that. Okay. The domain of g at x here this is just a linear function with a slope of 1 and a y-intercept of 4. This again is going to be xer. Okay, moves on for infinity. Okay. So now this part is a little bit confusing. If I read this initially, it probably won't make sense. The domain of f composed of g is the set of values x in the domain of g for which g at x is in the domain of f. Yeah, so it takes a little bit of understanding. So let's try and break this down a little better. So in this example, the domain of f is x is greater than 0, and the domain of g is xer. So the only values of g that can be used occur when g at x is greater than 0. So does this make sense? We can only use values of g that have x values greater than 0. Why? Because the original function here is only valid for x values greater than 0. So whatever this domain is, this is xer, the domain for this. We can only use the values that are greater than 0 because of the domain of f at x. Does that make sense? So our domain of f at x is limiting the domain values we can use of g at x. Does that make sense? Okay, good. So the only values of g that can be used occur when g at x is greater than 0. So therefore, we can set g at x greater than 0, and we can find out our domain. Okay, so now let's read that sentence again, see if it makes sense. The domain of f composed of g is a set of values x in the domain of g. So in the domain of g, so the domain of g is xer, so it's any values for which g at x is in the domain of f. And the domain of f is greater than, x is greater than 0. Does it make sense now? Okay. No? Read it 6 more times. Oh yeah, if it doesn't make sense, you can always look at the picture. See, so there's an x over here, there's a g here, there's this green circle with g at x in the middle, and then there's an oval circle around the green circle, which is apparently the domain of f, but it's also the range of g. I'm not sure about the diagram. Yeah, I couldn't understand the diagram. Okay, example 4. So now we want to look, this is what we're looking to prove. Here's the next example. Okay, another brilliant multiple choice question I could see. Is f composed of the inverse of f equal to the inverse of f composed of f? And what do you guys think now naturally, since we've looked at another scenario? This is probably going to be? Yes. Yeah, it's probably going to be equal, right? Yeah, just because the other one wasn't, and you can tell that these two functions are related already, right? Because one is the inverse of the other. So if you're substituting one into the inverse, or substituting the inverse into the original, you actually get the same answer, okay? So they show that algebraically. We'll look at it very quickly here. So here's our original function. Here's our original function. Remember, to get the inverse function, okay, remember how we do that. We switch the x and the y. So the first step is to convert this to a y. And then we switch them. So they did 2 steps here in one. They switched this to an x, and they switch this x to a y. And then you solve for y. Okay, so multiply both sides by y minus 2. These cancel out. You're left with 1 on one side. And you get this as the inverse. Okay, we need that because then we need to substitute into that value to figure out this over here. F into the inverse, okay? So next we're finding out, we're substituting in the value of the inverse here into the original function up here. So wherever I see x in the original function, I'm going to substitute 1 over x plus 2. So that's what I do over here. See this? 1 over x plus 2 goes in for x. Okay? That's what we do when we compose one function of another. We take the other function and we substitute it in. Okay? We rearrange everything and we get f composed of the inverse of f is equal to x. Okay? Now we're going to do the opposite. We're going to substitute in the original function, 1 over x minus 2, in for x in the inverse function. Okay? So that's what we're doing here. 1 over x minus 2. We rearrange and we get this. Okay? It's equal to x. Therefore, the original function composed of the inverse function is equal to the inverse function composed of the original function. All right, last one. Working backwards to decompose a composite function. So if we're given this complex function, we want to find two functions f and g such that h is equal to f composed of g. Okay? So the easiest way to do this is to make one function just equal to the original function minus one part of it. Okay, in this case we chose the absolute value brackets. So we set one of the functions g at x to x cubed minus 1. So we're setting it to the function that we want. And then the second function, we just take the absolute value of that function. That will give us the composed value